Hey everyone, my name is Tarik, and today I'll be talking to you about shipping production-ready Rust for Android. And to be explicit, I'll be speaking about shipping Rust code in an Android app and not delivering Rust to the Android operating system. There's a lot of work going on there that I'm not fully aware of, but that's not what the conference talk is about. It's about Rust code in the Android app. So just a quick introduction about myself. I'm a senior software engineer at Mozilla. You might know Mozilla as the company behind Firefox, and that's what I work on. I work on Firefox. Specifically, I work on Firefox Sync. So Firefox Sync is the system that gets your data from your phone to your computer and back, and from one computer to another. And all the data flows end-to-end encrypted, so nobody at Firefox can look at your data. And we do that because Mozilla is a very security and privacy-focused company. And as you may have guessed from the title of the talk, I work a lot with Rust. That's the cute unofficial mascot for Rust. His name is Ferris, and Ferris will be going with us throughout the talk today. And you can find me everywhere, as Tarik Eshaq, everywhere that I can be found. Please feel free to reach out after the talk as well if you have any questions or any thoughts about Rust or Rust and Android or otherwise. Very briefly go over what we'll talk about today. We'll give a general introduction about what Rust is for those of us who are not too familiar with Rust. And we'll dig deep into why it's incredibly important to the industry at large. Then we will narrow down into what everybody is here for today, which is when would you use Rust in Android? Naturally, we'll progress to how to use it. And then, because the title of the talk is Shipping Production-Ready Rust, we'll talk about a lot of the problems that come when you start using Rust in Android. And then from there, we'll talk about some remaining limitations that we at Mozilla are still wrestling with. So we'll start with what is Rust. So just a quick hands up. How many people here have heard of the Rust programming language? Sweet. It's the majority of the room. I love that. And how many people here have used Rust in a project or otherwise? All right. And how many people here have used Rust in Android? Hey, it's a few. Awesome. Well, hopefully everybody will have something to gain out of this today. So I'll briefly go over what Rust is, and then we'll dig deeper into how we use it in Android. So Rust, as most of you hopefully already know, is a multi-purpose programming language. It means you can use it to write a backend server, the same way you can use it to do what we're going to talk about today, which is ship it to the client on users' end devices. Like C, Rust has no automated garbage collection or runtime, which means that you don't usually have to ship a runtime or garbage collector with a Rust binary. It doesn't run on the JVM. It compiles directly to the CPU's native architecture. However, unlike C, Rust has what we call memory safety. It means no use after free errors, segmentation faults, or null pointers. It's a quick raise of hands. How many people here have had to deal with one of those issues? I'm so sorry. Like, honestly. Those are the worst to deal with. They usually don't show up until it's too late and are a big pain in the ass to debug. When I first learned that Rust can do both of those things at the same time, first I thought it would be impossible. Isn't that the whole reason why languages that run on runtimes exist, that have garbage collectors? They create that abstraction where users and developers don't have to worry about memory. So how does Rust do it? Short, compiler magic. I'm not going to talk a lot about the internals of how Rust does it. I'm not qualified to talk about the internals about how Rust actually does it. But we're engineers, or some of us are engineers, and there's no such thing as compiler magic. There's a lot. There's not an exhaustive list. But parts of what Rust does and does right is introduces new concepts such as ownership, concept of lifetimes, has a very strong type system, and I highly recommend for anybody who hasn't dug into Rust to read the Rust programming language book. It's open source, it's available online. Go through it, it's a phenomenal resource. But to give a bit more context into Rust, we'll show some examples of how it introduces memory safety. We'll be looking at C, and we'll start off with a simple function at the top. We have a function named f. If you're not familiar with C syntax, that first thing before the function is a return type. Returns this thing, which is an int star, a pointer to a 32-bit integer. And within that function, you assign a to 3, and then what you try to return is this ampersand a, which really means the address of a in memory. All the systems engineers are probably getting nervous right now. So what you're doing here is you're assigning a onto the stack, and you're returning its address to outside of the function. This can create all sorts of undefined behavior, and sometimes will work when you test it. And this is why we are moving towards memory safety. When you compile it, so GCC compiler, because this is a very simple program, will actually tell you, it will warn you, it will say that the address of the stack memory is being returned outside of the function. Please don't do that. Oh no. But it will still compile. And if you run it, you still get the correct value. Again, this is undefined behavior, just happens to be correct. So let's look at a similar program in Rust. So this is Rust syntax. So fn stands for function. That's an f function, and the name of the function is f. And the arrow means returns, and then or the return type. And the return type here is ampersand I32. It's the same thing, or not really. In C, we were returning a pointer, and here we're returning something called a reference. They're not really exactly the same, and I'll touch on that briefly later. And then we have let a equals 3, and then we return the address of a. Fairly similar to what we were doing in C. When we first try to compile it, the compiler will scream at us. And this is something that, if you've used Rust, you're very familiar with. You would struggle, you would fight with the compiler. That's a term in Rust when you're first learning. You would fighting with the compiler. And that's the compiler trying to guide you towards how to write code that is memory safe and works and satisfies all the guarantees that Rust provides. So the first thing it says is that this is missing a lifetime specifier. What the heck is a lifetime specifier? It's saying that, I'm going to read the help here for those who in the back can't read. I'm just going to read it out loud. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. See, the Rust compiler is smart. A reference in Rust usually means you're borrowing something that somebody else owns. And this function doesn't have any input, but its output is a reference. So the compiler is confused, what am I borrowing and how long does it live? And it can't infer that. It's suggesting we add a static specifier, and that really means here, Rust, I'm telling you that I expect that the return type to live for as long, or to possibly live for as long as a program can live. And if I try to give you something that doesn't, scream at me again. And we'll do that. We'll add the static specifier. Otherwise, it's the same function. And what we get is an error that we can understand. It says that you cannot return a reference to a local variable a. And that's Rust helping us make sure that we cannot do anything that will hurt us in the future. So now I've talked a little bit about Rust syntax and how it can introduce memory safety. And majority of other types of compiler errors that the compiler introduced will flow in the same way. You'd get an error. It's helping you along the way to get to working code. So why is memory safety important? And we'll go through a few statements from a few different organizations on how they've evaluated memory safety. Obviously, we're here in an Android conference. So this is an article from Android team in December of last year, where they've quoted that 65% of vulnerabilities across products and industry happen due to memory safety vulnerabilities. Those are the same vulnerabilities, a whole class of vulnerabilities that Rust eliminates. Chrome, similar numbers. This is in 2021. They said that last year they showed more than 70% of severe security bugs, memory safety problems. So this is not just a nice little win that Rust gives us. Those are severe memory safety problems that happen in practice that Rust helps eliminate. Microsoft, similar number. 70% of vulnerabilities they've assigned a CVE each year continue to be memory safety issues. Something about the 70% number that I don't think anybody understands, but it's obvious that there's a problem with memory safety, and Rust helps eliminate that. But it's not just those. AWS has said that they've adopted Rust, and Rust has quickly become critical to building some infrastructure. Meta has said the same thing, so they've embraced Rust. And each one of the organizations I just mentioned is a member in the Rust Foundation, and they're helping contribute to the growth of Rust as a language. So enough with just Rust and industry. Hopefully at this point, people are convinced that there is value here. I did jump over some things. Rust helps enforce memory safety if you use safe Rust, but that's not going to go into unsafe Rust in this talk today. So when would you use Rust in Android? Don't. So, and this is really not a don't for Rust, it's a don't for using native languages like Rust, C, and C++. Unless you would have used C and C++ anyways. And I'm going to go through some criteria where I think that would justify the use of a language like C and C++ and Rust. So the first is you have a desire to ship code to multiple platforms, especially ones that don't support the JVM. For example, you want to ship code to iOS. And maybe you lived before Kotlin multi-platform existed, and you just wanted to write code that ships to iOS. Using a native language would have been a great idea. But with Kotlin multi-platform, why not just use that? So the second criteria would be you wouldn't like to ship a garbage collector or a runtime. So there's a few reasons for that, and I would pause here and I would highly suggest if this is the reason you're using a native language, measure it. It's very easy to think that stripping away your garbage collector or your runtime is going to make your program more performant. So this is where benchmarking and measurement is incredibly important. So whether it's the performance or you would like granular memory management, and this is really where C, C++, and Rust shine, is you get full control over memory, where otherwise you're at the mercy of the garbage collector and whatever primitives it exposes. And the third one, that's the Rust-specific one. If one or two are true and you'd like memory safety, and I really hope that the answer is always yes, I would like memory safety. There might be some exceptions where you're missing some core platform support for Rust. The interop with whatever you're trying to do isn't there. But more generally, memory safety should always be top of mind, and that's where Rust comes in. So if all those three are true, that's when you would use Rust on Android. But again, I would caution, because in the rest of the talk, we'll go through some issues you'd come across when you start to introduce Rust into an Android app. But first, we'll go through how you'd use it, and we'll introduce it in 3 simple steps, and then we'll try to break those down into some problems. First, you'd want to compile your Rust code using the Rust compiler. Like I said earlier in the talk, Rust compiles to your native CPU's architecture. It doesn't compile to bytecode. It doesn't run on the JVM. You need to compile Rust using a Rust compiler. Then you'd want to link the Rust binary with the JVM application. This is where you'd use something like JNI, or you'd have to use JNI, which is Java native interfaces to be able to interface to outside of the JVM. And after you've been able to link the Rust binary, you want to be able to interface between your application code, your Kotlin, your Java, whichever, and the Rust binary from there on out. Seems simple. What could go wrong? Well, let's look through some problems that we've come across at Mozilla, and we'll try to go through problem and solution to kind of see to see how we've evolved, and eventually we'll look at what the system that we've designed to be able to ship Rust code looks like. So first, binaries can end up having duplicate Rust libraries. What does that mean? At Mozilla, we have multiple Rust libraries. We don't have an individual one. Each of those libraries has their own dependencies, and more importantly, each of those libraries depends on the Rust standard library, which is not trivially sized. If you're compiling each one of those individually, you end up with multiple binaries, with multiple dependencies, and possible duplication. That can bloat your application. What we've done is we've introduced this idea of a megazord. A megazord, if you remember Power Rangers, it's where all the Power Rangers at the end of the episode would gather up, turn into their machines, and merge together into the machine that has the better of them all. And in our context, the megazord really is a Rust library that imports all the other Rust libraries. And we do it precisely to remove the duplication in the dependencies. And we lean on our build system to be able to resolve conflicts. So this is a cargo.toml or a section of a cargo.toml file. For those not familiar, cargo.toml is a file that you use to configure your Rust crate, which is what a library is called in Rust. And all the Megazord is a bunch of dependencies. That's all. We'd include for example, for the sync example, you'd have your accounts, your sync, your push for push notifications. You would import all those. And then in the Rust file itself, all you're doing is exposing them. That's it. So the Megazord is just a thin layer with the pure purpose of removing duplicate dependencies. So what's the second problem? Integrating the Rust compiler with an Android build system is not an easy task. In Android, you're working with Android Studio. You could be running Gradle directly on the terminal. Regardless, you're working with an Android build system, not the Rust compiler. Luckily, Mozilla is open sourced, and we've had this open for a while, a Rust Android Gradle plugin that will run your compiler, or the Rust compiler, as a part of your Gradle tasks. And you can add that directly into your Android build system. And the problem that we'll be talking about the most today is that interfacing between Kotlin and Rust is difficult. And I'm going to introduce a new concept, or a concept that those not familiar with interfacing with native languages. And the concept is the concept of the FFI sandwich. I first heard this term, FFI sandwich, earlier this year at RustConf. It's a talk by Luke Frankel on GitHub and how they use Rust for GitHub search and interface into Rust from Go. And since then, it's been my favorite way of describing what happens when you interface across what we call the FFI, which I'll explain in a second. You usually have the buns. You have your Kotlin layer at the top. This is where your application programmers live. This is where the Kotlin code lives. And this is where you handle the application lifecycle and all that. At the bottom, you have your Rust code. This is where your Rust platform code lives. This is where your Rust engineer live. And this is the library that you're most likely shipping across different platforms. And you want to end up using it in Android. And in between those two layers, we can call the FFI, or the foreign function interface. Those allow us to interface between Kotlin and Rust, more generally between the JVM and the Rust binary. And in those two layers, we have a C-like Rust layer above the Rust code that exposes the ability to speak to Rust from any other C-like layer. And then we have a C-like Kotlin layer on top of that, underneath the Kotlin, that knows how to speak to a C-like library. And in brackets there, I put JNA. JNA stands for Java Native Access. It's a library that has helped us tremendously into using Java Native interfaces. And the reason we need those is because, again, Rust is compiled using the Rust compiler. Java, or in Kotlin, are run on the JVM as bytecode. Those two are not compatible because they have different, what we call ABIs, but I'm not going to go into that today. So what does a C-like Rust look like? You add a no mangle on top. So what that does is it instructs the Rust compiler to keep the symbols the same. So the function called sync will always be called sync and can be consistently referred to as sync from the outside. Then we add, so pub there just means public, and then we add extern C at the beginning. That tells the Rust compiler, hey, this function, treat it or compile anything that's exposed to the outside in the conventions that C would have. If you're familiar with ABIs, that would try to get as close to the C ABI as possible. And then within the function, it's Rust. You do whatever Rust you like. However, just having a function that syncs and just disappears is not really useful. Sometimes you want to get a result back. Unfortunately, once you're working with FFI, you are restricted to types that C, or types that are compatible with C. So in this case, we can expose a 32-bit integer, and that would be OK. But any type of complex types would require a bit more thought. And within inside, for example, you can have your implementation. Everything was OK. You've returned a 0, for example. If there was an error, you switch that to a status code. And then you'd have to know at the Kotlin layer all the way above how to convert that back into what it really was. That's where complexity starts to kick in. Unfortunately, usually we want to do things that are a bit more complex. You want to return values that maybe you can manipulate later. You want to return results. You want to be able to return more rich data than just a status code. So eventually, you could end up in a situation like this, where you're returning this star const u8, and that is a pointer. So that's the same thing that C knows and you'd usually use in C to return a pointer to the outside. And then you hope that the outside is smart enough to always pass it back to you whenever they need any information from it. Because again, the outside is running in JVM and not in your land where you have full ownership over that piece of memory. If you were to use the star const u8 in any context, in Rust, for example, dereferencing it, that'll be an unsafe operation. I promise I'm not going to speak about unsafe, but here I am. It will be an unsafe operation, and that's where memory safety starts to escape you a little bit. So this is exactly what you were trying to avoid when you're writing Rust code. So let's take a look at the layer above that, the C-like Kotlin layer that knows how to speak to the Rust code. That layer would end up looking something like this. You all are better Kotlin engineers than I am, so excuse if there's any issues here. But what we're doing here is we're implementing or extending a library abstract class. That's a type that's given to us by JNA, the library I mentioned earlier. You can read through it. JNA is very well documented. And what you do is you have to define how you would load that library. So you'd have to know the name of the library you want to load, and you have to understand how you would load it. Again, that's that middle step in our process. You need to load that binary. And at the very bottom, you have your functions that you've exposed. And that's the same name that you no-mangled on the Rust layer. And then that's the return type. And the example I'm going to use here is the status code example to make it a bit simpler. Then when you'd call it, you call the sync function, get your status code. If everything is not OK, you would need to create an exception, throw it up, that knows how to convert that status code back into something useful. It's a lot of complexity here. And if there's one thing to take out from this whole setup, is that there's a lot of ways this can go wrong. You can return raw pointers. There's a lot of very delicate code that programmers don't like to touch. So how do we fix that? Yeah, like I said, you're throwing away memory safety, you're restricting your types, and there's a large cognitive load. So how do we fix that at Mozilla? We took this FFI sandwich, and we turned it into this. Really, underneath that cloud is the same thing on the left side. But what we've done is we've created a tool called Unify to help us generate it. So Unify is open source. You can check it out. And what it does, or the best pitch I have of it so far, is Unify generates the inside of the FFI sandwich, so you all only have to worry about the buns. So Rust engineers can work at the bottom, Kotlin engineers can work at the top, and you can have the tooling do the things that you can get wrong. That's what tooling is for. So this is the new FFI sandwich, where there's a cloud you don't have to worry too much about. So the Rust layer, this is the Rust bun at the very bottom, would look something like this. This is your sync function, and what you're returning, you return a result. The result in Rust is an enum that is either OK or error. If it's OK, it includes a sync result. If it's an error, it includes a sync error. And this is exactly how you'd write normal Rust code. You don't have to worry too much about how to expose that to the outside. Then you define what we've called a UDL, which stands for Unified Definition Language File. And this defines all the functions that get exposed across the FFI. It's important to note here, this is the same file you'd use for Android. You'd also use it for iOS, and you'd use it for internal tools that we use in Firefox Desktop. So we have one definition file that knows how to be read by Unify to generate Kotlin code, Swift code, and others. And this is where the value starts to come in, and you're working across multiple platforms. In this case, you have your sync function, returns a sync result, throws a sync error. If you've worked with WebIDL before, you'd realize that this looks very familiar, and that's what we've adopted for this. Then you have your error, which is an enum, and it could be one of many variants. And you have a dictionary or data class, which is the result, and it can include a bunch of data. When you call it from Kotlin, you're writing plain old Kotlin. You're importing a function called sync, and that's the function that got generated for you. And when you catch, you're catching your sync exception, and that's the exception we've defined earlier. And its variants are exactly as you defined them in the UDL. So you don't have to worry too much about convergence. That's really how Unify works. So let's go back to our system as a whole and how it works. So you start with a bunch of Rust libraries. Those are your sync, count, push, whatever you want to call it. We put them into our friendly Megazord. That's the library that knows how, that imports all the other libraries. We use our Gradle plugin to help us compile that Rust code and generate generate a binary. And within that binary is a bit of Rust code that was also generated by Unify as a part of the build process. Then Unify as well takes input, those definition files that live with our Rust libraries, and generates a bunch of Kotlin files, one for each library, that know how to speak to the binary. They handle the loading, they know all the functions because they've read them from the UDL, and they can interface with it directly. So you, as a Kotlin engineer working on Firefox, you call the Kotlin code and only the calling code. For you, it's invisible, but a lot of that is happening underneath, or we at least try to make it as invisible as possible. You're just working with plain old Kotlin. And that's the principle with Unify, is that the Kotlin we generate, or the Swift, or whatever, has to always be, as much as possible, close to idiomatic handwritten code. But of course, it's generated code. So let's talk a bit more about some limitations. And those are remaining limitations with Rust and Android, as in those are things that we're still wrestling with today. Really, the limitations in native languages in Android, none of those problems is specific to just Rust. So let's take a look. One is restricted threading. The Android operating system is fairly strict with background threads. If you leave a background thread running too long and you don't control it and shut it off when it needs to be, the operating system will crash your app. And we've seen that in practice. So that means that we would have to make sure that we keep the Rust code living on a Kotlin thread or a Kotlin created thread, and we do not try to create more threads in Rust unless we know very well how we're going to shut them down. This is worse because it's difficult to manage the application lifecycle events from outside the JVM, so it's very hard for us to, within Rust itself, to control a lot of what happens with the threading. Second problem is that the asynchrony needs to be managed by the application. We can't use async runtimes because otherwise you'd have to ship an async runtime with Rust, and that's the whole reason we're picking Rust in the first place. That means that any I/O, and we have that in practice, any I/O that runs in Rust would have to block the calling thread. This can cause a lot of problems. Every Android engineer knows that you do not block the main thread. That's the one thing you cannot do. So that means that you'd have to be able to distinguish between blocking functions and non-blocking functions, and that's a communication layer as humans, or as documentation. That's not something that we have the current tooling for to enforce that this is a blocking or non-blocking call in Rust. So hey, Kotlin, please don't run this on the main thread. And this is, so it starts to become a problem of the caller needs to know, and if this needs to happen in the background, the caller needs to make sure it's happening in the background. And the last thing, and I would argue that this is the most important part of this, is developer experience. Yes, we have Unify that helps cloud over that section. Yes, we've tried very hard to make sure that it's as easy an experience for both Rust and Android engineers, but crossing over still happens. And crossing over creates friction. If you have a Rust engineer who's working on a core Rust project, crossing over means that they don't have the experience with a lot of the Android engineering. And it's same vice versa. So, and this is really, again, a general problem with writing native languages for Android. You'd have to be very careful about your developer experience and how your developers perceive the new system.